Before we talk about parametric and non-parametric tests, let me talk about confidence intervals for a couple of minutes. Chapter 13 presented confidence intervals for means and proportions, and it mentioned that confidence intervals are used for many other statistical procedures. Indeed, confidence intervals can be used for most of the procedures that we carried out in this text. As an example, in the special needs adoption study, the correlation between internalizing behavior, so that would be withdrawn behavior, and externalizing behavior, that would basically be aggressive behavior. The correlation between these two types of problem behavior for the adopted child as reported by the responding adoptive parent was 0.56. So that's a strong positive correlation. And the sample size was 746 and p equal 0.000. So there's virtually no chance that this result is due to chance alone. Therefore, we know that the null is likely false. SPSS statistical software computed a confidence interval for this correlation, and that confidence interval spans from 0.50 to 0.62. I mean, it's a 95% confidence interval, and we can be 95% confident that the population correlation is somewhere between 0.50 and 0.62. Confidence intervals, I mean, are just very useful. They're very handy. I mean, I actually like much more looking at the confidence interval than at the significance level per se. Confidence interval is telling you the likely range that the correlation falls in, and I find that more helpful than simply the probability that the relationship is or is not due to chance. But confidence intervals and significance tests provide complementary information. This text spent hardly any time on confidence intervals, aside from means and proportions, and I didn't mean to convey that these weren't important, and indeed I encourage you to have your statistical software compute confidence intervals in different situations. What's the distinction between parametric and non-parametric significance tests? I'm just going to add that in some ways I find this distinction to be a nuisance. I think if you understand the different tests and you can carry them out, that's more important than understanding the distinction between parametric and non-parametric, which is kind of a tricky one, and one that I think is actually difficult to describe in its entirety. The most basic difference: parametric tests assume that the population from which the study sample was selected has a particular distributional shape. On the other hand, non-parametric tests make no assumption about the shape of the population distribution. Pragmatically, most parametric tests, at least those that you encounter in introductory and intermediate statistics, most of these tests assume normality. And it's also the case that parametric tests are necessarily at the interval ratio level of measurement. I mean, you know, there's no a categorical variable, for instance, cannot be normally distributed. So when you're talking about a variable that has a normal distribution, by definition you're talking about a numeric variable. In other words, about a variable that is at the interval ratio level of measurement. And so here are some examples of parametric statistical tests that we have covered. So the large sample test of the mean, the 3T tests that we covered, ANOVA, the test of R, all of these assumed normality. Thus, all of these are parametric tests. Here are examples of non-parametric tests that we've covered. So for instance, the one sample test of P is non-parametric. That's the one sample test of a proportion. The binomial test is as well, as is the one variable chi-square test and the chi-square test of independence. Now, it's the case that the data, which is to say the information gathered for a non-parametric test, can actually be at any level of measurement. I mean, that's not what's going to define the test as parametric or non-parametric. I mean, a key distinction is that the information that the test actually uses is going to be almost without exception at the nominal or ordinal level. I'll provide an example now to show you what I mean by that. So here we have two groups of kids, and perhaps they've received some different kinds of interventions, and the goal of those different interventions is to help them stay in their seats at school. So here are the counts of the number of times the kids in each group get up out of their seats. So observe that n is small in both groups, and observe that in both groups the data is very strongly skewed in a positive direction. Now, a hint on the positive skew is to look for the outliers. So here's a kid who's been up out of their seat 67 times in this group, and 38 times in this group for one of the kids. So we've got positive outliers, and that's essentially the same thing as a positive skew. We've got a combination of very small sample size and very strong skew. In that situation, the independent samples t-test is not recommended. Well, a test we have not yet studied is the Mann-Whitney U-test. And the Mann-Whitney U-test is a non-parametric test. It is an excellent alternative to the independent samples t-test in situations where the independent samples t-test should not be used. Now, the Mann-Whitney U-test treats data as a rank ordering rather than as a count. So here is the data that will actually be used in carrying out the Mann-Whitney U-test. So each count is in essence transformed into a ranking. So let me just show you that where is the lowest ranked case, and the lowest ranked case is the 0. And so that's this case right here, the fourth case in group 1, has the lowest number of out-of-seat behaviors, and its rank is a 1. Let's find the second lowest number of out-of-seat behaviors. And the second lowest number of out-of-seat behaviors is obtained also in group 1. It's the first case, so it gets the second rank ordering. Where is the third lowest number of out-of-seat behaviors? And that is this case over here. Since this is the third lowest ranked case among the cases, it's assigned a rank ordering of 3. Now, I'll note that when the counts are identical, then tied ranks are assigned. So here are two identical ranks, and I'm showing you them here. Here are these same two kids, and they've been assigned a rank of 4.5. So these are the fourth and fifth lowest ranks, so to speak, and so we give them a tied rank. So rather than using the counts, the Mann-Whitney U-test is going to examine whether the ranks in the two groups differ to a degree that is greater than would be expected by chance. So the Mann-Whitney U-test is making no distributional assumptions. The fact that we've got such very strong skew, that's not affecting the Mann-Whitney U-test results. And so we're going to get an accurate P from the Mann-Whitney U-test because it's it's not using the the count data, but rather it's dealing in ranks, and we don't need to be concerned about. There are times when the parametric tests don't work well. Now, I mean, I can summarize that very easily. They don't work well when there is a combination of very strong skew and very small sample size. And in essence, in these situations, there's almost always a handy non-parametric alternative to the parametric test that isn't recommended. So for instance, the significance test of Spearman's R is a non-parametric test. It can have directional or non-directional hypothesis pairs. A significance test of Pearson's R examines the correlation between two rank orderings. Now let me just mention that in essence what the Mann-Whitney U-test is doing is looking at which rank, the rank orderings of which group are higher or lower. Is there a statistically significant difference in how high or low the ranks are? So the test of Spearman's R is examining correlation between two rank orderings. Spearman's R, the formula for Spearman's R is basically a shortcut formula for Pearson's R, and it actually yields identical values to Pearson's R when you don't have tied values. There are really two situations when the significance test of Spearman's R is used. So the first would be when interval ratio level data is highly skewed and sample size is small, in which case Pearson's R wouldn't be recommended. That's its most frequent use. And then also sometimes data is gathered in rank ordered form rather than at the interval ratio level, and that's also a situation where Spearman's R may be in order. I mean, its results will be more accurate than those for Pearson's R. I mean, its p-value will be more accurate when you have very strong skew and very small sample size. Sometimes you have association between two ordinal level categorical variables. Chapter 7 presented some examples of such. When you have directional association between two ordinal level categorical variables, we presented each of these four measures of the size of directional association. And all of these measures can be tested for statistical significance, and you do so using statistical software. For each of these measures, hypothesis pair can be directional or non-directional. The non-directional null for each of these is that the measure equals 0.00 in the population. This slide presents some non-parametric tests for independent samples. We've already looked at the Mann-Whitney U-test. The non-directional null for this test states in essence that the ranks in two groups are equally high. The hypothesis pair can be directional or non-directional. And this is your excellent alternative to the independent samples t-test when sample size is very small and skew is very strong. The Kruskal-Wallis test extends the Mann-Whitney U-test to situations that involve two or more independent samples. Its hypothesis pair is non-directional, and this is an excellent alternative to ANOVA. Here are some non-parametric tests for dependent samples. The Wilcoxon signed ranks test is used with two dependent samples, and it is an excellent alternative to the dependent samples t-test when this test can be inaccurate, and that would be again, when there is the combination of very strong skew and very small n. Now, the sign test is another alternative to the dependent samples t-test. And it would be preferred over the Wilcoxon test when you had a categorical ordinal level dependent variable. So, I mean, basically, if you had numeric data and it was highly skewed and sample sizes were small, then the Wilcoxon signed ranks test would be the way to go. On the other hand, if you had ordinal level dependent variable and two groups, you'd go with the sign test. An example might be your dependent variable is rate the class, excellent, good, fair, or poor. And you have two groups rating the class. And again, they need to be dependent groups. And so perhaps it's one rating at time one, and then the very same people make another rating later on in the class, and you compare those ratings to see if the class ratings have gone up or down. Sign test would be the preferred test there. McNamara's test tests a difference in percentages between two dependent samples. Non-directional null would be that the percentages in the samples are equal. So as an example, suppose that you work in a medical clinic, and that in the month that precedes the addition of paraprofessionals to your team, 25 of 50 clients keep their appointments. So in other words, 50% kept their appointments. Now then, paraprofessionals are added to the team, and we observe this very same group of 50 clients. I mean, this is the key. The two samples are dependent. And then following the addition of the paraprofessionals, that is to say in the next month, 35 of 50, or 70% of clients keep their appointments. So appointment keeping differs in the 2 months. You want to see whether that difference is a large enough one to be statistically significant. And again, our samples are dependent. You would carry out McNamara's test, and in this situation, with the non-directional hypothesis pair, P calculates to 0.044, and that is indeed less than 0.05. We'll presume that was our selected significance level, so we would reject the null that pre-paraprofessional and post-paraprofessional percentages are equal. The change in percentages in this example is indeed unlikely to be due simply to chance. Should you carry out a parametric or a non-parametric test in some given situation? Now, if you're dealing with categorical data, by definition, you're going to be carrying out a non-parametric test. So this question then boils down to presuming that you've got interval ratio level data, numeric data. Should you carry out a parametric or a non-parametric test? This is going to be a difficult question to answer. Different people disagree on this. You know, I would say clearly if your sample sizes are very small, and I'll just pick a number out of a hat. If they're less than 15 or so, and if in combination you've got extremely strong skew, say you've got extreme skew as demonstrated by the figures in Chapter 5, well, there you should probably go with the non-parametric test. If either the sample size is moderate to large or the skew is not extreme, those factors certainly tilt you towards the parametric test. Now, some of the advantages of the parametric tests are, they're much more commonly used than our non-parametric tests. And by more commonly used, I mean they're more. That's given that we're dealing with interval ratio level data, then it's much more likely that the researcher will use a parametric test. As already mentioned, if you've got categorical data, the non-parametric test is used by default. The parametric tests are quite robust to the normality assumption. Oftentimes they have greater statistical power. That's not always so. They're certainly more straightforward. We've not examined yet multivariate statistical procedures, but parametric tests sort of lead naturally into multivariate procedures, and the non-parametric tests aren't in general as well connected to more advanced multivariate applications, though in some ways that's changing all the time as we get more sophisticated. Here's the author's preference: when possible, stick with a parametric test. Next, we're going to take a look at data transformation.